The final model we'll look at before we get to the hydrogen atom, and one that is closely related to the hydrogen atom, is what's known as the rigid rotor. And so this is a model for looking at rotations of molecules. And sort of the model that we imagine is that we have two masses, in this case two atoms, M1 and M2, separated by some distance r that's fixed. So that's the rigid part of the rigid rotator. Rigid means that r is fixed. This molecule cannot vibrate at all. And this system is free to rotate in three-dimensional space. We can do this problem in looking only 2 dimensions as well, but we'll look at the full 3-dimensional problem. Okay, and so that's sort of the model we have. Is we imagine we have a diatomic molecule that's free to twirl around in space. And what we're interested in are what are the possible energies that are allowed. Because what we'll see is similar to all the other systems that we've seen, the energies are quantized. This molecule can only spin at specific speeds, which is really weird to think about, but that's how quantum mechanics works. And so what we'll do is we'll consider the potential energy, I'll write x here, but it's really depends on all the variables. We'll consider potential energy to be 0, right? It doesn't take the potential energy is 0, but r is fixed, right? And so we can imagine that there's like an infinite potential barrier to keep the masses from moving relative to each other. This is a little bit like the particle in a box, right? We constrain the system to a specific situation. And so the Hamiltonian, if we want to solve this, we need to have the kinetic energy plus the potential energy, but we'll say, okay, that's 0. So then the question is, how do we write the kinetic energy? So everything we've considered up to this point has been looking at linear systems, where we kind of have something moving along a line. But now we're looking at a angular system, right, where it's not the distances that matter, but the angles at which things move that matter. The angular momentum is going to matter. And so when we're looking at angular systems, kind of starting place is comparing linear and angular systems. So we can describe angular things that move, that rotate in physics, and this is done all the time. In linear, we have linear systems, we have variables that we use to describe our system. We have x is position, we have m is mass, p is momentum, and v is velocity. And in an angular system, we have corresponding variables that kind of match these. So theta, the angle, is similar to the position. It represents how far has a molecule spun or a system rotated, whereas in a linear system, it's how far is a object moved along a line. The mass is equivalent to I, the moment of inertia. And so mass tells us how hard is it to move an object. Moment of inertia tells us how hard is it to spin an object. Instead of momentum, we have L, the angular momentum. And so this is the momentum of an object spinning rather than an object moving in a straight line. And instead of velocity, we have omega, which is the angular velocity. So how quickly does something spin? What's the rate of change of the angle as a function of time? All right, and so let's go ahead and define a couple of these. So I, the moment of inertia, the definition of this is for all the masses that are part of our system, so from I equals 1 up to n, however many there are, we add up all the masses times their distances from the axis of rotation squared. So r here, r sub I, is the distance from the axis of rotation. And you may have, if in physics, you may have calculated some moments of inertia for different types of objects. In this class, we're going to look at just one type of object, specifically, this idea of a diatomic molecule rotating about this axis here. All right, so we'll have m1 that is a distance r1 from the axis, m2 is distance r2 from the axis. And so we'll say I is equal to m1 r1 squared plus m2 r2 squared. Now it's not a terribly convenient way to write this, and so we'll make some definitions. We'll define r to be r1 plus r2, right? That's just the total distance between our two masses. And we can show that we can use the reduced mass that we used for the harmonic oscillator, shows up again. We can combine these and show, I'll leave this as an exercise to the reader. Problem 5-29 in your textbook goes through this. But we can show that I equals mu r squared, right? So for our particular system, this is the definition of the moment inertia. Now this is not a generic definition, right? The most general definition is this one up here. But for our system that we're going to talk about in this class of a diatomic molecule, we use I equals mu r squared.